Today we are going to see coding on convolutional neural network. Simply we called as CNN. So I have just in Jupyter notebook I have just opened the source code and I will be explaining with the source code first. After that we will see what happens. So now to start with, we have this import torch.neural network optimizing packages. Torch vision is for images, and the images can be converted into the tensors called through transforms, and the data sets we just wanted to read from the data sets, and the utilities like data loader, which is loading from secondary storage to the model. And we'll be plotting some of our results. So we wanted to use matplot library, which is can be plotted through Python scripts. Now this is the first one. Next thing is we have a CNN model. We just define a class called a CNN model, that is inheriting the property from the module class, which we call it as a neural network NN. As we know that CNN has three kinds of layers, that is a convolutional layer, pooling layer, and fully connected layer. So now we wanted to use a convolutional layer, and which is then pooled with the maximum pooling, two-dimensional pooling, and again we go for another convolution layer with again maximum pooling we just go for. Then after flattening the curve, we will go for the linear FC1. FC1 is a fully connected layer. Then after that we scale down further to FC2, that is a fully connected layer number 2. So if you see here, we have this convolution 2D here. We have one is the number of input channels and the number of output channels. So input channel is generally for a black and white picture, that is the mono picture. Usually it will be 1. If it is for a color image, it will be RGB. Since it is 3, so it will be 3 here. For a black and white picture, it will be 1 here. 32 is the number of features that we can able to get from this, get from the input image. So this is what the output image. Kernel size is 3, means which is the 3x3 image in convolution layer. We can see that 3x3 means a 3x3 matrix will be the kernel, and that is a kernel size that we are going to scale down. Stride means the kernel 3x3, how much it moves. How many pixels it moves. It moves one stride, means it moves 1 pixel at a time. So that's what here it is stride. Similarly, padding equal to 1 means outside of the image it will be adding 1 extra pixel, so in all the sides. So that's why we have this padding number 1. If you want to add 2 pixels, then you can add padding equal to 2. So this is what the convolution layer, 2-dimensional convolution layer will do. After that we go for a rectified linear unit. So this is just to discard the negative values. We wanted to take only the positive values. The negative values will always be considered as 0. Then after that maximum pooling size, which in 2 dimensions is the kernel size 2 and stride is 2. So you will be having a maximum pool size. So maximum pooling means of the matrix value whatever we will be getting, we will take the maximum value of among the 4 or 5 or 6 or whatever be the case in the matrix. So stride is also equal to 2. So that means both together we will have a 2 by 2 matrix. Similarly, in the next convolution, this 32. So you can see that the features 32, it becomes 64. Now the input channel is 32, because from this previous layer it was 32 as the output. That will be fed as the input here 32, which will become 64, and kernel size 3 here. Now stride is 1 here and padding is 1 here. Then again we go for a rectified linear unit. Then again we go for a maximum pooling of 2 bar 2. Then after that, after this 64 output channels, we just flatten this image, and that 64 which was multiplied into 7 into 7, which many number of features will be getting, and that can be converted into 128. So now this is where we have the linear curve. So this linear value 64 cross 7 cross 7 features will be converted into 128. So we can have any number here, 256 or anything, but 128 being the optimal value we just use. Then after that this is being sent to the rectified linear unit, because this at this place also we can capture only the positive values, the negative values we just discard. Then finally we come to a conclusion on 128, 10. So this 10 is that the data set what we are going to use is fashion mn ist, so which is having only 10 classes as an output class. So since the final output will be 10 only among the 10 classes, that is 0 to 9, we wanted to have our output over there. After these 10 classes, so we just give this forward function. So forward function, we just send the self.convolution 1 and apply the rectified linear unit number 1 and maximum pooling 1 as the first layer. Second, again convolution number 2 and ReLU 2 and maximum pool 2. So finally after the 2 layers we go for flattening the values, then going to the fully connected layer 1, then again applying the ReLU 3 and fully connected layer 2. So that's how the way the class CNN model is activated. So this is a simple procedure to do that, but after the return X means the image will be returned over there. Now we go for the random seed for reproducibility. So we will be setting the random seed here. So that is to randomly generate the values over there. Now we have the fashion MNIST dataset. We just load the fashion MNIST. So here we are going converting everything into tensor with the normalization value of 0.5 comma and 0.5. So actually tensor is nothing but we usually read about scalar, vector, matrices, and finally we can say tensors. So 0 rank tensor will be called as scalar, and first rank tensor will be called as the vector. So tensor will be have multidimensional data. So that's what we are going to transform. Now we have the fashion MNIST dataset. Since fashion MNIST dataset is so common, so we have by default Python packages to import that thing. So we are importing 2 datasets. One is a training dataset, another is a testing dataset. So training dataset totally have 60,000 images and testing dataset totally have 10,000 images. So where we will be downloading everything to the ./data. That means a data folder will be created, and inside the data folder all the dataset will be completely downloaded. So training equal to true, download equal to true, transform equal to this thing, and here training equal to false, and download equal to true, and transform equal to transform. So now we have the data loader here. So batch size equal to 64. So now this 64 means that we can have batch size of 64, 120. That means every time whenever we want to read the data, so we will be reading 64 at a time or 128 at a time. So that's what we will be doing that. So now 64 is the default data batch size that we want to give. And in the training data set, when we deal with the data set, so train data set is an image, is the variable name. Here there is an object name, and batch size equal to batch size, which is nothing but 64, and shuffle equal to true. So that means while training we can able to shuffle the complete data set. Okay, and the testing side we again use the same batch size. So if you want to complete the job in a faster bit of faster training, if you want to give, then you can give the 128 also as a batch size, so that at a time 128 batch numbers will be fed. So that's how the way it go. Now initialize the model. So we have the CNN model here. We initialize it. We define a variable name model, and again we have a optimizer, and again we have a loss function here. So here cross entropy loss means, so generally loss will be measured from 0 to 1. So 0 is for the minimized loss and 1 is for the highest loss. As far as possible in our system, we will be trying to move the value towards the 0, so that it will be a better system, because the loss is almost equal to 0. But practically loss may not be 0, but we are trying to approach to 0. Similarly, Adam is one kind of it's an optimizer model. So where to minimize the loss function, we just use this Adam. But we supply a learning rate also. So 0.001 is the learning rate. We can adjust the learning rate also for the machine to be trained. So on all these aspects, the CNN model will be working out. Now training loop is we use the number of epochs. So now when we go for the training, so number of epochs means we just move from the data set completely. The model visits the data set once, means one epoch. If the data set is read twice, it becomes 2 epochs, 3 epochs, like that we have 10 epochs. So that means all the 60,000 images will be read for one epoch, means it will be read completely one time, then second time, third time, like that 10 times we have just given. We can adjust these values also. This number of epochs is one kind of a parameter where we can able to do the tuning. So now as per the number of epochs, what we do is we just to go for a optimizer and output the model images. So whatever we are going to read will be just sending as an output here. Now at every 100 steps we will be displaying the images, that is visualize some images we just display. So totally 4 images to be displayed every time, and with the images with the labels also. So labels means what is the name of the image and what is the label of the image. All these things will be displayed. That means the labels will be 0 to 9, totally 10 labels. So among that, which label we are currently printing and what is the name of the image. So those things will be listed out there. Using the matplot library we will be displaying. So then finally for testing the model, this is testing the model, we are just doing the testing, and the testing here is we will be computing the accuracy there. So how much accuracy we are going to get from our the CNN model. So now in this case the accuracy here is predicted accuracy. We will be having a prediction also. We will be having the correction as well. Now in this example we are going to see what is the image been provided and what was the prediction in the first level of epochs, in the second level of epochs how we do, in the third level of epochs how we do. So that's how the way we are going to do the model. So now finally we'll be printing the accuracy in terms of the percentage. So that's what we are going to see. Now in our model we are going to have totally 10 epochs. So let us run this example. So what we do is just there's a play button here, just click this run button. So now for the first time when you are running this button there, the images will be, the data set will be downloaded from the internet. It might take some time since I have already done it once. So already the images are downloaded. So for me it just goes to the epoch now. Now the epoch is printed in terms of the step, each step based on this value. We can see I plus 1 modulo 100. So number of epochs, epoch plus 1. So every time the epoch is incremented by one number. So that's why I am having 1 of 10 here. Now you can see that you can see this is one kind of an image where you can see it is a kind of a jerkin or something, and here the last also the jerkin. So both resembles almost the same. You can see the label given as number 2 here, but the prediction is number 4. Here label 9 prediction 9 and label 4 prediction is 0. So that means whatever it was label 9 but predicted as 0. So now this is the problem in this label here. So likewise now we can see the epoch 1 of 10 here, the number of step is in 200, and label 5 prediction 5 0 and 3. Now since this sees that it is not having a clarity, but label is 0 but predicted as 3. So that's how the way the prediction goes. And you can see every time the loss also minimized. So you can see 0.6373 6372, then 41 it was reduced, but again finally the loss is increased here. So 0.7 is a huge loss because it approaching towards 1, so which is not supposed to be a good system or a good model. But let's see at the final moment, since we are given 10 epochs, let's see what happens here. So since it is fashion MNIST, we have some 10 classes of images, and this all the images will be shown like this. And let's see, you can see one epoch still running, and now see that the second epoch started here. Now second epoch, so up to one epoch the loss was 0.2934. This 2795 was the first epoch gets over. Now second epoch started, and you can see here second epoch, and at every epochs and every 100 steps we just display the images what the machine have learnt. And now the third epoch have started here. So second is over 3.3584 and the third is started here. So likewise this simulation might be taking some time till it gets completed. So let's wait. Almost the 10th epoch have started here. So let me show you. So far here it is up to 9 epochs. We have 1961. Now the 10th epoch started here, 1287. And you can see sir, for one time it was 0.0222, which was a very good minimization of loss function. And so here it is 0188, still more or less. And let's say the final thing. So final is 0.1814. So if you take the average, it may come with almost to 0. And you can see the test accuracy is the testing image accuracy. You can see here it is 92.13%. So this is what the accuracy what we get in this data set. Now if I give the more number of epochs, maybe the overfitting might be one problem, but might be the testing accuracy may be improving, but the optimal value of the number of epochs is only just 10. So in case if you want to change this value instead of 10 to, let's say if I go with only with let's say 2, so I just go with the number of epochs as 2. Now let me run it here. Now we can see only 2 epochs. Let's see what is accuracy over there. So 1 of 2. So now there are so many error messages there. The prediction was wrong. First epoch is getting over now. So second epoch is starting now. let us see our accuracy. What was the accuracy? Now you can see the accuracy is 89.77%. So even for 2 epochs the accuracy was 89.77%, because now what I did is the same data set I have been running for a quite number of time, and all the trained data set is there in the data folder. So what happens is as I keep on having these images, so the accuracy will be improving quite a lot. So if you are doing for the first time, maybe you cannot get this much accuracy, you can please try on that. So this is an example of a convolutional neural network. So in case we want to change the hyperparameters, so the hyperparameters are, the first hyperparameter is the batch size. So this is one of the first hyperparameter where we can able to tune it. Tune it means we can able to modify these variables from 64 to 128. Let's say if it is 32, what happens? That is one thing. And number of epochs we can able to see. If we have already we have 10, now we have converted into 2 there. So what was the accuracy when the number of epochs is 2? So number of epochs, it takes less time to complete, but accuracy also will be minimal here. Similarly, the third one is the learning rate. So 0.001. So this is the third one, hyperparameter tuning. So 0.001 means the learning rate. So if we want to make the faster learning, means we can able to use 0.01, so that the learning factor is too high. But sometimes if the learning factor is too high also, maybe there could be some loss of data over there. So that is the third one. And fourth one is the neural networks. So here if you see, we are using only 2 convolution layer here. So con1 max pool 1, con2 max pool 2. In case if you want furthermore, you can use con3 and max pool 3 also. Then after that you can go for the fully connected layer. So this also one kind of this completely this becomes one layer. Then this is second layer, and we can have one more third layer also. So as per our convenience, we can increase the number of neural network. So in those, if you increase the number of neural net convolution layer there, what happens is the time taken, because one convolution layer and max pooling layer involves a huge number of multiplication and addition operations, which will become a time consuming process. So those places you need to have a GPU rather than a CPU. Now what I am running here is only, I have a laptop with only a CPU, no GPU there. That's why I have just taken this much time. So likewise, these are all some of the hyperparameters that we can able to tune it. So this is all about this convolution neural network. Thank you.